This lesson is on systems of equations. We're looking at Chapter 8 of the McGraw-Hill-Ryerson Pre-Calculus 11. We're going to center on sections 8.1 and 8.2 simultaneously, and these are the things that we expect students to know at the end of the lesson. I do encourage you to stop, press pause, rewind, do the questions as you can, and then check back into the video for the answers, so that way you're engaged in the learning process. We're looking at outcome RF6, and it does help that if we draw from our grade 10 work, which was solving systems of linear equations. And if you feel that you need a refresher on that, then you should look at some videos that deal with systems of linear equations first. So we're going to start with this introductory example. With this example, we have two equations. The first one that we see, which I'm going to circle here in blue, this one is a line, it's linear. And the second one, which I'm going to circle here in green, this one is a quadratic. So we're going to graph these and let's see what they look like. So right onto this graph here is my line, and then I have my quadratic, my parabola. And so I've drawn these, but the whole idea is for this lesson, it asks us to solve this system. This is a linear quadratic system. The solution to a system is the point or points of intersection. So in this particular case, this point, which is 0, 3, and this point, which is -2, -5. Both of these points are the solution, because if you remember back to grade 10, the point of intersection, and there was only one point when you had linear and linear, but we have linear and quadratic, we could have these 2 points. So this would be the solution to the system. Well, let's go a little bit further from there. Here is a parabola. So I don't have a line to go with it, and I'm asking you this question. What linear equation can give you only one solution if it's graphed with this quadratic? See if you can come up with an equation. I anticipate that most of you would have one of these two, and the first one I'm thinking of is this one. So it only has one point of intersection, and that point of intersection that we're hitting happens to be at the vertex, which is -2, -5. What's the equation of this line? Well, this line is x is equal to -2. It's a vertical line. So you probably took a vertical line through the vertex. If you didn't take a vertical line through the vertex, then the next one that I would anticipate that you probably would have taken, well, this one green, is this line, the horizontal line through the vertex. And this has the equation y is equal to -5. I will note that both of these have at vertex as the point of intersection. There is other lines that are also will work that will only give one point, and those are called tangent lines. And tangent lines lead us into calculus. So we could have a tangent line at any particular point, and then you have one point and only one point of intersection. Let's move on. Let's try another question. This one is the same parabola. Now we want you to write a linear equation that will give no solution when it is graphed. Can you come up with one? Well, I just quickly came up with this one, and I said, okay, I could easily just quickly have this line. This line, if it extends, it's never going to meet the parabola. So there's an example. You could have a line right here. That one works. It could have a negative slope. You could have one over here. There's multiple correct answers. That just gives you an idea. We just need to know that the line and the quadratic can never meet because we're asked for no solution. So this is that first introductory example that we did graphically. So we already know what the answer is, but let's see, how do we solve this algebraically? So algebraically means we're going to have manipulating our equations. So back to looking at some of those things from grade 10, we had two methods that we used in grade 10 to solve systems of linear equations besides graphing. We had substitution and we had elimination. And we could use either one for this scenario, but this one's set up nicely already. If I have y equals an expression, that's set up nicely to do a substitution. What I would do is I'd take the 4x plus 3 and I'm going to substitute it into the other equation for the y value. So I'm doing a substitution on the play. So this would give me 4x plus 3 is equal to 2x squared plus 8x plus 3. And now I'm going to solve for x. So I particularly like to have a positive x squared. That's just my preference. So I have 2x squared plus 8x minus 4x plus 3 minus 3. So all I'm doing is I'm subtracting 4x from both sides, and I'm subtracting 3 from both sides. And I'm simplifying, and I get 2x squared plus 4x is equal to 0. And when I factor, I have 2x and then x plus 2. We have to remember, what does that information give us? Well, that tells me where x is equal to 0. X equals 0. Let me do this. 2x equals 0, or x plus 2 is equal to 0. When we do the math, we see that x is equal to 0, or x is equal to negative 2. Okay, we are not done though. What's our answer? It is the point of intersection. All we have found with these two are the coordinate points for x, but we don't have the full coordinate point. We just know the x coordinate. So we have to find what the y part is. So we could go back to our original equation, which is y is equal to 4x plus 3. Substitute in the value of x that we found. So this one here is 0. And we get y is equal to 3. So that is telling me one point. So the point that this one has in common is 0, 3. Or we also have where x is equal to negative 2. So y is equal to 4x plus 3. Y is equal to 4 onto negative 2 plus 3. Y is equal to negative 8 plus 3. Y is equal to negative 5. Y is equal to negative 5. The other point is negative 2, negative 5. So we have 2 points of intersection. That makes sense. That's what we had graphically. So if we just go back to what we had with that graph, we see that our 2 points that we had were 0, 3, and negative 2, negative 5. Sometimes it's easy to do from a graph, but sometimes having a graph is not that easy or practical. So that's why we need to have that strength that we get from the algebra, which is what we have here. Let's look at a second example. So here are our equations. So this tells me I have two quadratics, and you could sketch these by hand, draw them out. I'm going to use the technology, and let's look at the graph and let the graph tell us what the solution to the system is. Okay, so here are our two quadratics. What is the solution? The point of intersection. Now there's the point of intersection, and that point is 3, 5. So what's the solution? 3, 5. There's 1 point. These particular parabolas are transformations, more specifically, they're translations of the same parabola. So because of that, they only have this 1 point of intersection. Well, what would that look like algebraically? So can I use algebra to solve that same problem? And I've just rearranged these equations a little bit, and they're set up nicely for us to look at elimination. So we'll just show you elimination. Remembering that when we do elimination, you're adding negatives, you're trying to eliminate variables. So if you're subtracting, all the signs need to change. It's like multiplying by the -1. And I'm looking at this, I'm saying, okay, look at this. Here's the y, here's a y. 2x squared, 2x squared. I want to subtract so that the variable is eliminated. Because of that, I have to do a sign change. So this becomes negative 2x squared plus xy, sorry, plus 8x plus y plus 11. And when we work this out, we see that 2x squared, negative 2x squared, that gives me 0. I have negative 16x plus 8x, that's negative 8x. Negative y plus y, there's another 0. And I have negative 35 plus 11, which gives me negative 24. And it says, oh, x is equal to 3. But we're not done yet. All I know is the x value. I don't know the y value. So I am going to use one of these equations and put in the value for x to be 3. So I'm going to use the bottom one, 2x squared, negative 8x, negative y is equal to negative 11. And I'm using the original before I did the sign change, but you can use the sign changes. So this is 2 times 3 squared minus 8 times 3 minus y is equal to negative 11. So this is 2 times 9 minus 24 minus y is equal to negative 11. So I have 18 minus 24 plus 11 is equal to y, just rearranging what we have. So 18 minus 24 is giving me negative 6 plus 11 is 5 is equal to y. So for our final answer, we have the coordinate point 3, 5. This is our final answer. That is the point they have in common. And we know that we've shown that previously with the graph. Example 3. Here are two parabolas. Let's graph these. And these are nice. They're in vertex form, so that's going to make this very easy for us to do, especially just to do a sketch. I'm going to use my graphing software. Interesting. The solution to this system, remember what does solution mean? The solution, or to solve the system, are the points, the point or points of intersection. Do these two meet? Never. They don't. They are really sort of translation on each other, right? So one is vertically translated. Because they will never meet, they have no point in common. So the answer is no solution. There's no point in common. Well, what does that look like algebraically? What would we expect to find? Well, we're going to do the same procedure. Now, because these are in vertex form, they make things a little bit harder. So what we would do is to expand them. And you'll note I even expanded this one right here, but I kept all the fractions, and that just makes it a little more cumbersome. So we're going to make it so there are no fractions. To do that, I'm going to multiply every term by 2. So just keep in mind that we've got this equation goes to x squared plus 2x plus 2. And then this one goes to here. But I'm going to multiply every term here by 2. So those 2's cancel out. These two cancel out, so they give me 1. So what I have here is 2y is equal to x squared plus 2x minus 3. And at the same time, on the left, I have y is equal to x squared plus 2x plus 2. And this is set up quite nice for substitution. So I'm going to substitute this value of y into this y. So this would, and I'm going to need a little more room here. So 2 onto x squared plus 2x plus 2 is equal to x squared plus 2x minus 3. So I have 2x squared plus 4x plus 4 is equal to x squared plus 2x minus 3. And I get x squared, and I have 4x. Add 2x, I have 4 add plus 7 is equal to x, is equal to 0. And I can't factor that, so I might have to do a little bit more work with that. So I'm going to take this graph off because we need more space. Let's see if I'm able to do that. All right, so I'm going to take this equation and I need to solve it. So this is a quadratic, x squared plus 2x plus 7 equals 0. It's not factorable, so that means that I don't have integer or rational roots, but I could have irrational roots, or I could have no real roots. I really do prefer to have, this is set up nicely for completing the square, so I'm going to complete the square. So what makes this a perfect square is if I add 1, but if I'm adding it, I also need to subtract it. So this is that mathemagic thing happening. We're just adding a 0, just in a different form. Add the 7 equals 0. So I have, this is a perfect square, so that's x plus 1 squared plus 6, because I'm adding these two together, equals 0. So I have x plus 1 squared is equal to negative 6. I can take the square root of both sides. Let me do that. This. So I have x plus 1 is equal to plus or minus the square root of negative 6. Taking the square root of a negative, therefore, no real roots. So no real solution. So algebraically, if it's a no solution, you're not going to be getting that real number. Going to stop right here and then look at part B that will look at a little bit more of the word problems in depth.